Okay. So welcome to the latest Saguki meetup. We're really thrilled to have Paul Dorfman presenting for us, who has written who is probably the world's foremost expert on hashing in SAS, along with Don Henderson. Written a great book, very detailed, to tell you everything you could ever imagine you might need to know about hashing. And today we're going to look at using hash functions to partition data into independent groups. So with that, I'll hand to you, Paul.
Hello, everyone. Thank you for having me. This talk is called using hash functions, but actually has nothing to do with the hash object. When Ellen said that we're specialists in hashing, you probably meant hash search, hash aggregation, and all this kind of thing. But actually, this one has to do with hash functions, surfaced in SAS, but nothing to do with the hash object, okay? Or any other hashing for that matter. So the presenters are nominally yours truly and Don Henderson, a friend of mine. Both of us hail from USA, or formerly from Ukraine, and we are co-authors of the book that Ellen just showed you, data management solutions using SAS hash table operations, a business intelligence case study. Okay. All these things are credentials just to hide our inadequacies. So, you can read through it for a couple of seconds if you want, and then we'll proceed to the crux of the matter. All right, I think that's enough. All right. So, oftentimes, a SAS programmer or analyst or developer faces a problem that has an input to process in some kind of way, manner, or form, and this input is just way too large for resources. Just imagine a file that has like 100 billion records and gobs of variables, and you want to aggregate it, by a whole bunch of composite keys and whole bunch of variables, and hopefully do it in one pass. Well, the normal way of going about it is first is just get more resources. But it is system limited. It is limited by the capacities of the organization. So the most normal obstacle is just it's rare, feasible, and often it's unfeasible. So you can ask for memory, all you want, but it depends on how much money your organization has. And so then, this clever programmer says, well, I'll go the divide and conquer route and just split this input into smaller segments and then process each segment separately. And then simply add the output for each process, to the final result, right? So that's done from time immemorial. The dinosaurs in this room, would know that when we were working on mainframes and always shared resources that always were extremely scarce. Okay. So fight again, over the disk space, sort work and things like that were commonplace those days. So let's look at a sample task of segmented data aggregation. The techniques presented here, would actually focus on aggregation, but they also work for other tasks such as joining, sorting, subsetting, whatever. So the question is, if input is too large to aggregate in a single pass, can it be done in multiple passes? Let's just look at a simple query in ProcSQL. Let's say now we have some kind of file called trans, and we want to get the sum of some variable var, okay, by the composite key, ID, and key, and also count distinct values of var within each unique value of this composite key. Okay, so if you have like 100 billion records or a view that actually brings in, let's say, 1 trillion records, and you simply throw it at SQL, most likely you're going to fail because the optimizer won't optimize correctly. it probably, may start sorting behind the scenes, and basically you just throw it at the SQL and it runs forever and goes nowhere. This kind of talk arises from a practical task that Don and I faced with a couple of clients, and what I've just described was exactly the case. Okay, so we are focused on aggregation in this talk, just an example. Once again, this technique can be used for basically any data processing. When we try to do things this way, there are basically two critical criteria. My first criterion is that, which is absolutely required, is that we need to segregate the input in such chunks that no key value present in one segment must be present in any other segment. Okay, because otherwise, if we're dealing with a sum, we'll have to resummarize. That is possible at the end. But however, since we're dealing, for example, with count distinct, like here, we cannot resummarize anything because count distinct is a not additive statistic. So that means that if you want to summarize by some kind of key, that key had better be in one segment. So then, we can add the result of processing the segment to the final result. And the second one, of course, that we must ensure that all segments have more or less same number of records or unique key values. Because if we have an input and then we separate it in one chunk, that let's say 1 million records, and one segment has 900,000 records, and the rest have 100,000, basically defeats the purpose. So how to achieve this? Well, sometimes it's possible to do based on a priori knowledge about the values of key components. For example, you may know from your business knowledge that if you separate all the database based on the first digit of account number, it will separate the database evenly in equal chunks, more or less. Okay, so it may be available, but may not be available. Most of the time, if you don't have such a convenient key, okay, then of course, this kind of thing must be validated. It'll be time consuming, and like I said, it may not be available at all. Well, the second way actually presented here in this talk, okay, is mapping the segments using a hash function. This is the focus of this presentation. The advantage of this method is that you don't have to think about what properties your keys have, okay? And it works regardless of how the key values, be it simple key or composite key, are distributed. So let's get into the bottom of it. Well, normally, if you deal with real data, the composite key values in large inputs are diverse and numerous. What it logically means is that within those key values, there exists some combination of their bits or bytes whose values split the distinct key values more or less evenly according to some kind of rule or formula or algorithm. We know that this kind of rule is kind of there, but we don't know what it is. So that's the problem, because we don't know neither the combination nor the formula, okay? And there is no business rule that says, well, do it this way. So here is the idea. We don't need to know, because instead we can use what is called a hash function, okay, to map those input key values into a string. Let's call it H key, hash key, okay? It doesn't matter how it's called. And to do it in such manner that first, key values map to H key in a highly random fashion. Well, this, of course, will be automatic because a hash function has the property of being highly random. That's what hashing is about. And that's actually why it's called hashing. And then this hash function must have a different property, which is critical for this application. And it means that each unique key value should map to one and only one unique value of H key, meaning that there should be one-to-one correspondence between the composite key on one hand, okay, and the hash function response on the other hand. Okay, if that rule is broken, nothing of that will work, and we'll see later why. Then we can use some part of this H key to assign each record of the input with a segment number from 1 to some kind of predetermined number n. Now we can actually choose that n arbitrarily, and then use that segment number to split the input into n key independent segments. For example, you can do it via where clause, but there are other ways. You can do the if, you can do the actually index and all this H key and so forth. And then aggregate each segment independently, as we have described earlier in this talk. You can do it either serially or in parallel, depending on how your system is set up, or how you want it. Okay, so how do we use the hash function? And first, let's just grab the composite key and concatenate its components. We use a delimiter in this case, the semicolon. It's critical, but we'll discuss it later. If it's a simple key, of course, we don't have to concatenate anything, or we can stick this key into the getText function, and then, of course, if it's a numeric, it becomes character automatically. If it's character, it will remain character. And then pass this result to the hash function MD5 and obtain its 16-byte digest H key. Why MD5 we'll discuss later. Okay, it's just one of SAS hash functions. There are a whole bunch of them now. Okay, they're all rendered now through the function called hashing. Okay, and so MD5 is the first one, actually, historically, the simplest one as the quickest one to execute. One of the reasons to choose it. Okay, what it produces, if you execute this statement right here, H key equals MD5 concat. Okay, what you get in response, you get a string whose first 16 bytes are non-blank and the rest are blank. So the MD5 function grabs its argument concat and returns the H key, which is 16 bytes long. Okay? So you can actually combine these two statements into one in this manner. Now, instead of MD5, I can use SHA-256 and a whole bunch of other functions, but we'll talk about it a little bit later in this talk. So suppose that we have something like that as completely concocted case, we call it trans, which is our input file. We have an ID, which is character, key, which is numeric, and then numeric variable var. And we want to aggregate it just as we described above. Basically, we find the sum and the distinct number of distinct values of var, okay, by the composite key ID key. So now let's create our hash key here. So the goal here is to demonstrate the properties of this hash signature, or as it's called otherwise, hash digest H key. We'll create a test table, says dataset, map, to show how the distinct key values ID key map to H key. Just execute this simple SQL step. Here we have the formula for our H key right here. Okay? So what we do, we concatenate ID and key over the delimiter column, then MD5 it, and arrive at H key, which is a character variable length 16, but it's more convenient to look at it, in hex, because otherwise what you'll see is gibberish. I'll execute it. No, that actually can be view, if you want to avoid the disk footprint. And that's what we have in response. So the H key is actually a 16-byte variable. Okay, each of these hex digit, double hex digits corresponds to 1 byte, and I just separated them so that you can see them. Okay, so notice now that this H key byte values, basically, have a random pattern. The input keys, if you look at the input file, kind of ordered, and they follow each other. So but here it's completely random. You look at any byte of this byte, or this byte, or this byte, and you see that the keys, the H key values assigned to the pair of ID key are highly random, okay? Which will add us with segmentation. And then how do we, now we have to create a segment to assign to each pair of HD key. So how do we do that? Well, we can pick actually any combination of bytes here from H key, or any byte for that matter, okay? Let's, for example, pick, I don't know, byte 10, for example, byte 10, right? And so we'll create a variable, one byte variable called H byte, okay? Which is simply, the 10th byte of hash key H key. Okay? Now let's obtain its rank. Now it's just numbering in the collating sequence. Okay? Either of these formulas right here will work. Okay? If we wanted to grab 2 bytes, now we have PAB2 and so forth. And they use a simple format formula to split the ranks into segments from 1 to n. So no matter what we have here, we can have rank equals input H byte like PAB5 or PAB6, and we can grab like 6 bytes, right? But then this formula will distribute those values, those will be high values, okay, into the segments from 1 to n. Oh, now if we do that, what we'll have here is we have ID key, H byte, the rank, and then the segment will look like that. So you see, from the simple example, that actually this segment, okay, will be distributed more or less evenly across the ID key values. Now, of course, you have like 10 billion of those, you'll have different number of unique keys in each segment, but because of the randomness or the hash function, it will be distributed evenly, throughout all the segments. Evenly, I mean more or less. Let's demonstrate, for example, it. Okay, so after all that is done, we can basically do our aggregation for each segment separately, as for instance here in this sequel right here, and then append the result to the final result. Well, basically, for each segment, we calculate this formula, for the H key, then plug it in here, with the where clause. So each segment selects the records. Each segment selects the records from the input correspondent to its value of H key, okay, aggregates it, and then appends it, to the final result, and then just call this macro. Of course, you can do it in a variety of different ways. By the way, hi, Don. And you can do it in a number of different ways in SAS. There are many ways to skin that cat, but it's just an idea here. So the results of aggregation here, if we run this against this sample trans data set, okay, is if we do just one single query, straight query, we'll get these results, and those results in blue, and if segmented, we get those results in yellow. Okay, but they're exactly the same except for the sequence of the records. So, for example, if you have the ID key A1 here, you have your results here, sum and count, so 9, 1, and so forth. So only ID key orders are different. That's not the problem, of course, because normally aggregated files are indexed by by the key. Okay. For example, in online applications, when you actually want to look at all this aggregation later.
Paul, could I just interrupt 1 second? I thought it was me, but on the screen, there's kind of a box, and it might be the list of attendees. I don't know if you're able to collapse or the Zoom windows.
Oh, you mean you can see it on my screen?
Well, no, we just see a black box.
How about this?
That's much better.
Oh, yeah, so much better for me too, because I didn't want to spoil anything, so I didn't touch it. But
there's another one on the top.
Right. But I thought, you actually guys, didn't see it.
Yeah, maybe we missed this.
Sorry. Okay.
But there's also another one along the top by the title. I don't know if it can be minimized.
Yeah, go.
Thanks, Phil, for pointing that out.
Yeah, I know this. You mean this one?
Yes.
Yeah, you may be able to drag it if necessary.
Well, maybe it can drag somewhere. So okay, if I drag it here,
full screen maybe.
It won't be that bothersome, right?
That's much better. Yeah.
Oh, yeah.
Better.
Yes.
Oh, yeah,
Thank you.
Thank you for pointing it out, Alan. Okay. So the trans, of course, is a little small file. Okay, so let's see how it works with a file with more numerous and diverse distinct keys. So in this case, it's completely concocted out of my feeble mind with 1,816 records. Okay, and let's pick the number of segments equal 3. Okay. And what we have in the result, after we do the proc freak on the segment, we will see that, for example, if we separate the input in 3 segments, that's what we'll have as a result in each segment. And if we pick 4 segments, that's what we have. So even though we see that the number of records falling in each segment is different from the other segments, in the balance, they're almost the same. Okay, from the standpoint of massive processing, we can say they're actually the same. Now, this kind of approach works with any aggregation method. Let me try to, okay, any aggregation method. So here we use SQL as a result, but it can apply to anything. It can be sort, control, break, meaning sorting and then determining what the aggregates are. You can use actual the SAS hash object, the means procedure, and so forth. Just use this method as the core of the macros, %seg ag, shown above, and you'll be fine. So, for example, let's consider the example of sort, control, break. So, for example, here we have a sort. We are sorting this particular segment, okay, and then we go using the dow loop here, okay? Computing the sum and count distinct, okay? And this will work with this kind of method just as well as a scale, maybe even better. Who knows what the optimizer throws at you. Okay, Don, do you want to actually chime in on this one? No, I guess Don doesn't.
Sure. The whole point here is that the technique that we're talking about is completely independent of the data. It really doesn't care what kind of data it is. Paul and I have used this technique on point of sale retail data. I think Paul referenced earlier using, one of the ideas was to use a digit in the customer number to partition the data. We've used it for financial transactions, for insurance claim data. I think the insurance claim data example, Paul, was our first one. We had to figure out a way to partition the data because the job had to run nightly and it took 67 hours. So a nightly job that runs for 67 hours isn't exactly an option. So yeah, it really doesn't matter what kind of data you're talking about. And that's the advantage of this technique. You don't have to know anything about the data.
Thank you, Don. Well, now, how to choose the number of segments and how to not use to choose the number of HK bytes, that we use to create the segments from. Well, if we create n segments, that means that we have to pass through the input basically n times, even though we use the where clause, okay, or maybe an index, it's still extra processing. Okay, so this number of segments have to be chosen sort of like judiciously. So that we reduce the resource usage in each pass, to an acceptable level. For example, if we're using the hash object to aggregate, we shouldn't run out of memory, okay? Or, can be true to a degree with proc mean summary. While at the same time, we want to avoid overtaxing the input output with too many passes through the input data. As far as choosing the number of bytes is concerned, we just can choose the very first byte. Is the simplest way to do, okay? Because one byte, potentially has 256 different values according to the number of characters in the collated sequence. Okay, we can split the input, into 256 different segments, using just a single byte. We can use 2 if you want to allow for a 256 times 256 split. Okay, but you're never going to need nearly as many segments, and of course you don't want to have as many passes through the data unless you have some kind of quirky system that excels at parallel processing. Right? So practically speaking, the simplest thing to do is just to select the number of bytes from H key, from 1 to 4, and then n as a power of 2. So you would have like 2, 4, 8, 16 segments. But of course, if you want to have something that is not power 2, the mod formula will automatically handle the n split, regardless of how you choose double. I have to mention here also that instead of choosing 1 byte, you can actually use the in format that's called bits, okay, to choose the bits. So for example, if you simply choose the first bit from H key, it will automatically spread the input into 2 segments because the bit has only 2 values. And if you pick, like bits 2 in format, then you automatically split it in 4 segments, even without using the mod formula, and so forth all the way until 8 bits, which is W equals 1, when you have 256-way split. Now, what is crucial in this process is to ensure that the methods we're using map our keys, to HQ1 to 1. Okay, that's because we want the input segmentation, to be key independent. Okay, which means that no key value in one segment should be present in any other. Otherwise, this kind of scheme won't work, especially with select distinct. And this key independence, it can be mathematically proven that it rests entirely, okay, on the fact that the hash function maps its argument to its digest in a one-to-one manner. So you know that what we do to achieve that, we first concatenate all process key components into a single variable, okay, and then map this concat variable to HQY hash function. So in order to make this mapping unique in the end, the concatenation must map the process one-to-one, and then the hash function must map the concat to HQ one-to-one. Okay? If one of those conditions are not met, then we won't have what we need. There's no breach of one-to-one mapping is allowed. So the first component here is hash function uniqueness. As many people would know, MD5 is the hash function. The 16-byte signature is known to have what is called a vulnerability. So in principle, meaning theoretically, it can map 2 different arguments to the same signature. This is termed a collision. And people just throw their arms in the air and say, well, we can that function because we cannot guarantee uniqueness. But let's take a little sober look at this thing. And the 50% chance of getting one MD5 collision, okay, is 2 to the power of 10, 2 times to the power 10 to the power of 19, which means to see just one collision, we have to execute MD5 200 quintillion times against 200 quintillion distinct arguments, or execute it 100 trillion times per second for 100 years. So practically speaking, it means that you will never see a collision with using MD5 function ever. Okay? It simply never happens. It's just like when you have basketball, there's one chance that all the molecules of this basketball inside it will spontaneously collect in one part of it, in one half. but you know that practically it will never ever happen. Now, if you want to be completely bulletproof, you can use the function SHA-255-256, which has no known vulnerabilities, has no collisions. However, it executes about 20 to 40 times slower than MD5. So given the chance of how minuscule the chance of MD5 collision is, as far as I'm concerned, and I'm sure done, it doesn't make any sense to use it instead of MD5.
I agree, but one point about the 20 to 40 times slower is if you pre-process the data to add that, so you're only doing it once, so it could be that the processing time for whatever it is you're doing outweighs that. So, that's really a business decision you need to make. But once again, the likelihood of a collision is so small. And the other thing to think about is, what is the impact of a collision? It's probably pretty trivial.
Thank you, Don. So now the second part of achieving uniqueness is to make sure that when we concatenate the components of the composite key, we don't get one too many situation. Well, we know that we use the catx function. It's 200 by default, so we have to provide enough length for it ahead of time. Use the length statement, and so that there would be no chopping or trimming, chopping of this value, within the buffer. Okay, so. But just remember that longer length is actually reduced execution speed. Okay, hark back to what just Don said about that in this regard. And now a more serious obstacle arises when we delimit catx improperly. Because first of all, we should never use catx without a delimiter. So use catx, not catas. And then we have to choose a delimiter different from the endpoints of any key component. Okay? We may not know those ahead of time. Okay? Now, I mean, we don't want actually to go through the whole input to find out what are the endpoints of each key component. So, the bulletproof approach, to avoiding this kind of collusion is to surround each key component with two characters different from the delimiter. You can look at the paper at SAS Global Forum or at the article on sascommunity.com, okay, where this is presented, and kind of go into gory details of how it's done. Okay? But it can be done, okay, and it's bulletproof. You actually have these two characters; they can be the same, okay? Or they can be different, some like in pairs, like left bracket, right bracket. And now we have to thank you from Paul Dorfman, which is yours truly, and Don Henderson, whom you just heard. Thank you so very much. Have any questions?
Yeah, thanks very much. We've got a comment from Quentin. I guess if you use the hash function for splitting, but not the aggregation, then there could not be an impact from the collision.
That's absolutely true.
Okay. Any more questions from the audience? Then what I would do, I will stop the video and say a very big thank you, first of all.
Okay, and I'll stop sharing.
Yeah.